Hello, hello. Welcome back to Dr. Deegan Does Physics, or welcome if you're new here. I'm Dr. Corinne Deegan, and I'm about to get into doing some physics. So this video is going to be the solutions for the problems I posted earlier this week. The problems themselves are posed as a review for students who already took Physics 1 and are going into Physics 2. These are just a couple of the concepts and types of problems that you'll tend to see again in Physics 2. So if you are taking Physics 1, there's still a good thing to look over so you have an idea of what's going to be coming back around if you have to take Physics 2. And they're just, there's still questions that you'll see in Physics 1, so they're still viable for all of that. I apologize for getting this upload up a little late. I'm still kind of new at this, but I appreciate you being here anyway. And yeah, let's jump into the solution. Our first problem was just an algebra question with a little bit more of an involved question. So we're trying to isolate and get this t out of that exponent and by itself. So there's a few different ways that you could approach this problem. I'm going to start off by just getting the exponent by itself. So I'm going to divide both sides by that n0 or that n naught, depending on how your professor likes to pronounce it. So we'll get that n over n naught is equal to that exponent to the minus, that symbol is lambda times time. And then to get rid of that exponent, or basically get everything that's up, raised out of that exponent, we're going to take the natural log of both sides, since the base of the exponent is e. So then the base of the log we want to use is going to be the same as the base of the exponent that we have here. So if this was, I'll kind of do off to the side. So if this was instead, say, like 10 to the x, and we wanted to get rid of that x, you would do a log base 10, and then you would get back basically whatever was in that exponent, and the log base 10 and that exponent base of 10 would cancel each other out. So that's the same thing that we're going to do here. So by applying the natural log to both sides, we'll end up with natural log n over n0 on the left, and then we'll have that minus lambda times t on the right, and then we can divide both sides by that negative lambda to get t by itself, and then just to rearrange it with t on the left, we'll get that t is equal to ln n over n0 all over that negative lambda, and then that would be your final answer. So yeah, so you're not going to see this probably until a little bit later in Physics 2. In Physics 1, you have a little bit of like needing to know the log rules for that operation as well. But the most important thing is knowing that to get the variable you want outside of the exponent, you're going to have to apply a log of the same base to pop that guy out, to pop whatever the exponent is out and bring it back down to just a normal line. But yeah, that's question 1. Question 2, we're looking at a centripetal force and uniform circular motion question. So for those of you who did take Physics 1 and are now on to Physics 2, this will be a topic and a concept that comes up again of having a centripetal force acting on a particle so that it stays on a circular path, and then being able to relate or find out characteristics of that circular path, mainly the radius of the path, the speed at which the particle is going around the path, and you could also solve for the centripetal acceleration as well. And then if you are in Physics 1, well, this is something that you will see again in Physics 2. So make sure you pay attention. First thing, I'm just going to read through and try and pull out some of my givens in this question. So we have a force of 10 newtons is keeping a 2 kilogram particle on a circular path with a rotation frequency of 60 rotations per minute. And we want to know what is the radius of the path. So this is typically how I like to set up my problems. So we know we have a 10 Newton force. We know it's keeping it on the circular path. So I'm also going to just put in parentheses that this is a centripetal force from the information we have. The mass of the particle is 2 kilograms. And then they give us the rotation frequency. So I'm also going to write that out in 60 RPM. And then we want to know the radius. So I typically also like to write whatever variable or value I'm looking for with the question mark and then circle it just so I have kind of a goal post that I know I'm working towards. I don't know that it's absolutely necessary for this problem, but it's a good habit to draw a picture so we know the particle is on some sort of circular path. I'll just pick it to be on this side. It doesn't really matter. We know that we have some force acting to keep it on the circular path, which means that the force has to be pointing towards the center of the circle. We'll also have our acceleration pointing in that direction because that's also necessary to keep this on a circular path. And then, I don't know, I'll just draw an arrow to indicate that this thing is going around in a circle. So first thing I want to do is our standard unit for time is seconds, not minutes. So I want to get this RPM into basically hertz. So it'll be counting that frequency in the standard unit for frequency, which would be 1/seconds, which would be relatively easy here. We can write out, so I'll change the way that RPM is so that it's rotations over minute so that we can more easily set up that conversion factor. So we'll have 1 minute over 60 seconds, which will give us basically those minutes cancel. The 60s will also cancel based on the numbers that I chose here, and we'll end up with 1 rotation per second, but I'm just going to write that as hertz because as soon as you end up with something being counted over seconds, then you can write that in terms of hertz. So that gives us that frequency. And then before we do anything else, I'm going to set up what I know that I can use, which is going to be the fact that I have this force. I know that I have this acceleration and this force that's keeping this particle on this circular path. So I'm going to set up Newton's second law for the centripetal forces and acceleration. So we'll set up Newton's second law. So that's the main physics that we're going to be using here. So that would be the sum of the centripetal forces is equal to mass times the centripetal acceleration. The only force we have here acting in the centripetal direction, direction in quotes here, basically pointed towards the center of the circle is all I mean by that, is that F equals 10 newtons that we have defined. So I'm just going to write that as F. And then for those of you who may remember, we have a definition for the centripetal acceleration in terms of the speed and the radius. So the magnitude of the velocity squared over the radius of the circular path is going to be equal to that centripetal acceleration. So I'm going to go ahead and make that substitution in this step as well. You might even on some equation sheets or some professors will just leave it as F equals mv squared over r. So just this is my reminder of where that v squared over r comes from. And now you might be thinking, well, we have F, we have m, we need r, but we don't know v. So how are we supposed to solve this? Well, we don't know v explicitly, but we can get v from the frequency, the rotational frequency that we have. And we can approach this 2 different ways as well. So the easier way to do it is just using an equation, which some professors will give you. I feel like some don't, but it's 2 pi r times the rotational frequency will give you the velocity. So we could, because then you would have that F, we could just plug this whole quantity in for v inside of that v squared, and then we would have our equation in terms of all variables we know plus only one that we don't, which is what we're solving for. So we could go ahead and go that route. The other thing I'll just show you or point out, because I sometimes don't always see professors giving that definition of the speed for uniform circular motion in terms of that rotational frequency. So the other thing you can do is you can set up a conversion. This will get a little funky with the variables, but 1 rotation going around this circle in terms of length would be equal to the circumference of that circle. I can scroll up so you see that. So basically, if I were to go around this circle once, that would be 1 rotation, but that would also correspond to traveling the length of the circumference of that circle. So we can kind of set up this conversion factor that 1 rotation is equal to the circumference, and then you can take that one hertz that we have, so that one rotation per second, and we can multiply it by 2 pi r over 1 rotation, so that the rotations cancel and we're left with 2 pi r. So yeah, I don't always like the way that this ends up being, because then this is going to be over a unit, but the unit could also just get kind of absorbed within, since I don't have the units written out for the radius yet either, so we can kind of just ignore that unit for the time being. But you end up getting the same answer. I just wanted to point those out. So I'm going to do the easier thing since it's easier to explain, and I'm just going to use that equation. So I'm going to set the m over r by itself, and then inside that squared we'll have 2 pi r times the frequency. That whole quantity is squared. The next line, I'll distribute that squared to everything in the parentheses. So we'll get m over r 4 pi squared times radius squared times frequency squared. Now one of those r squareds will cancel out with that r in the denominator. So we'll end up with force equals mass 4 pi squared times radius times frequency squared, and then since we want radius by itself, we'll divide both sides by everything apart from that frequency. And I'm also just going to rearrange this into kind of a more conventional order. So we'll have 4 pi squared m over frequency squared, and that'll leave us with force. I'll just rewrite it all out. All that stuff is equal to r, and then I can plug in, I should have room, 10 over 4 pi squared times 2, oh, I lost a squared on that frequency, times 1 squared. And I'll go ahead and plug that all in to my calculator. 10 over 4 pi squared times 2 times, basically that would just end up being 1. And this gives me a radius. I'm going to round to 2 sig figs of 0.13 meters. And then just because of how small of meters that is, you can also put that in centimeters, which would just be 13. But it'll kind of depend on what you're being asked for. If you're told specific units or if you can use whatever you want, either answer is correct. Last question we had is a little bit of a complicated one. I'm probably going to have to do 2 pages for this one. This will be familiar to you once you start getting into your Coulomb's law questions and your electric force questions, because they like to do these kind of geometric setups with a few different particles where you are finding the net force or something like that. So we're first going to re-practice and revamp our skills by looking at how we would do a problem like this with gravitational forces, which you should know and love from Physics 1. And if you are taking Physics 1 right now, then this is just a question that you can use, and keep in mind that questions like this will come up again in Physics 2, and you take it if you take it. So for this, we are ignoring all forces except the gravitational forces between the particles shown below. We're going to calculate the magnitude of the net force on particle 1. Each particle is considered a point mass of 1 kilogram. So I'm just going to and that's our picture, so everything's rearranged. We have the distances between 1 and 2. We have the distances between 2 and 3. These guys are connected on a line. 2 and 3 are connected on a line. And then I'll just draw this other line connecting 1 and 3, which we don't know for sure. And then I'm going to put some labels on this. So the distance between 1 and 2, so I'll call that r subscript 1, 2 is equal to that 8 centimeters. We are going to ultimately want this to be in meters. So if we have 8 centimeters, there is 1 meter for every 100 centimeters. So that should give us 0.08 meters. So we'll have 0.08 meters for R12. For R23, that'll be let me write that up here first. So I'll call R23 the name for that 7 centimeters. And then you would do the same conversion factor just to get that in meters. You should get 0.027 meters. And then, so that's all I'm going to do for this. And then the only other thing I'm going to do at this moment in time is I'm going to write out M1 equals M2, which equals M3, which equals 1 kilogram. So you could also just define all of these masses to just be M without any subscript on them, since they all have the same value. That isn't always going to be the case, that they always have the same mass, so I am going to leave the variables more general, but in other questions, you can always simplify to make it easier for yourself. Okay, so then the other thing I want to do on here is I want to draw our forces. So if we are looking at the gravitational forces, the net gravitational forces acting on particle 1, we're going to have one gravitational force pointing from 1 towards 2. That'll be from the gravitational attraction between those two particles. So I'll call that F12. And then we will have another force acting from 1 pointed towards particle 3. That'll be the attractive gravitational force between those two particles, and I'll call that F13. This is getting to be already a pretty small picture, so I kind of want to blow up what's going on at point 1 so we can draw out these forces a little bit more cleanly. So if this is our particle 1, I'm going to exaggerate these a little bit. This will be our F12. Our F13 we'll say is going off over here. You have to break this down so that F13, so F12 is already going along just like the conventional negative y axis, but F13 is going off at an angle. And before we can get our net force, so I guess we want F net on 1 is what we're solving for, which would, from just vector addition, our F net should be equal to the vector sum of F12 and F13. But because this is a vector sum, that actually corresponds to the x component of F net being equal to, if there was an x component of F12, I'll still write it generally, F12x plus F13x. So the x component is equal to the sum of the x components. The net y component is equal to the sum of the y components, and we have to do some trig to get those components and then to recombine to get what the actual net force is. So we have quite a number of steps. My apologies. So what I'm going to do first, this F13, I'm going to draw an angle here that I'll call theta at the top, which will be the same. I'll draw it on the other picture too, even though that one's going to get messy, just so that we can see how it relates to those distances and that like dotted triangle that I have for those distances. I'll draw the x component, F13x, and then I'll do the y component in a highlight over here so that it's not quite the same. And I'll also do that label in purple so that we know the difference. So that gives us kind of ultimately how we would get the net force, but we first have to find what the magnitudes of that F12 and that F13 are, and we're going to get that from using the definition of the global gravitational force. So F12 is going to be the easier one, so I'm going to do that one first. I'll probably have to do F13, I think, on a different page. But the definition of the global gravitational force generally is, we have Newton's gravitational constant times the mass of one particle times the mass of the second particle divided by the distance between those two particles squared, and then the sign will be pointed towards one mass, away from one mass and towards the other, like we have drawn. So we have all of these values. We do have from the picture, we know that the magnitude or the direction is going to be negative in the negative y, but this formula will just give us the magnitude. So then for F12, I'll typically rewrite the general equation with the variables that I have defined. It just turns out for this first one, my variables are the same. So cool. And then I'll plug in the values that we have. So G is just a constant, 6.67 10 to the minus 11. The masses were both 1 kilogram. And then our distance is going to be that 0.08 meters squared. And I'll go ahead and put that into my calculator. And that gives me we'll do 3 sig figs, I guess. Probably only should do 2, but I'm going to do 3. 1.04 times 10 to the minus 8, and then this should be in newtons. So then I'm just going to circle that because we're going to need it for later. Then we can do 1.3. Again, this is just going to be the magnitude. So if I was being strict with my notation, these should all have absolute value bars around them. Most of the time I'm not. So our variables here, big G is the same, but now it's M1 and M3 divided by their distance, which I called R13 squared. Actually, I didn't name that yet. Okay, this is why this is the more complicated one. So, and I am already pretty messy on this page, so I am going to go on to another page. My apologies. On here, I will deal with the R13. So this distance between 0.1 and 0.3 is what I'm going to call R13, which we do not have explicitly. However, the points 1, 2, and 3 are all sitting on a right triangle, and we have 2 sides of that right triangle. So we can find R13 using Pythagorean theorem. We are eventually going to need to get that angle as well, so that we can do that vector addition to get the net force. So I think I'm just going to do both of those things in this little box that I set up for myself on the bottom left. So we can say R13 squared is equal to 0.08 squared plus 0.07 squared. We take the square root of both sides to get that R13 by itself. And then I'm just going to do that whole thing in my calculator. So square root 0.08 squared plus 0.07 squared is going to give me, this one I will round to 2 sig figs. So we'll get 0.11 meters. So we'll circle that. And then we also need that angle at the top. I typically like to use whatever I was originally given. So since I was given the adjacent and the opposite side, I'll do tan theta. It's going to be opposite over adjacent, so that'll be 0.07 over 0.08. I don't have enough room, but you would take the inverse tangent of each side to get theta by itself. So theta is going to be inverse tangent 0.07 over 0.08. Let me make sure my calculator, oh, it is in radians, weird. Make sure my calculator's in degrees, and then I'll do tan inverse of 0.07 over 0.08, and I get 41 degrees. Okay, so we'll keep those 2 things, and then on the next page, we'll set up F13 equals G M1 M3 over R13 squared, which will be 6.67 10 to the minus 11, 1 times 1 over, what did I just say? 0.11, and then that's squared. I'm going to use the unrounded number in my calculator since I just have it right here. So this might give you a slightly different answer if you're using the unrounded number, but I get 5.9 times 10 to the minus 9 newtons. And then this is the one that we're going to have to break up into an x component and a y component. So this one I'm just going to draw by itself. So I'll do a new picture where that's our magnitude, that's our y component, that's our x component, and then that was our theta up here. So if we do that, our y component is the adjacent side, our x component is the opposite side. And then this will just give us the magnitudes, and then we'll have to put the signs on, the directions on the vectors themselves, since we can see y is pointing down and x is pointing in the positive x. So let's see. So we've got our SOHCAHTOA. I'll do y first. So y is adjacent. So we have adjacent over hypotenuse is going to be equal to cosine theta. So we can multiply both sides by that hypotenuse to get it out of the denominator, and we'll get that y component by itself. I'm just going to move that F13 in front of the cosine theta, and then we'll have 5.9 10 to the minus 9 times cosine of 41. Again, I'm using the unrounded stuff that's in my calculator just since it's easy for me to plug that stuff in and work with those numbers while I'm typing it out. I'll still round to 2, so I get 4.4 times 10 to the minus 9 newtons. I'll go ahead and circle that one since that'll be something that we need. And then we'll have the opposite side over hypotenuse equals sine of theta. Do the same thing, multiply each side by the magnitude f13 to get that out of the denominator. And then we'll have f13x equals f13 sine theta, so 5.9 times 10 to the minus 9 times sine of 41 gives me 3.9 times 10 to the minus 9 newtons. So the other thing that we could have said that I didn't write out was the fact that f12x is going to be equal to 0 and f12y is just going to be equal to whatever value we found, 1.04 times 10 to the minus 8. And I guess again, these are all magnitudes that I'm dealing with here. I do not have the directions put on these. So when I do go ahead and set up f net x will be, there is no x component for f12, so it'll just be the x component for f13, which is already in the positive direction. So I will put a plus outside that magnitude, and then that'll just be equal to that 3.9 times 10 to the 9 newtons. Our f net y is going to be negative, should really be more consistent with this notation, but negative f12y, negative the magnitude of f13y, and then I'm going to do that addition in my calculator, which gives me this one all round, negative 1.5 times 10 to the minus 8 newtons. And then lastly, now that we have the net x component and the net y component, we can combine those to get our magnitude. So our f net will be f net x squared plus f net y squared, and then this should all be under a square root. We can put in our values, negative 1.5 10 to the negative 8 quantity squared, 3.9 times 10 to the 9, negative 9. I lost a negative 9. That's important. Quantity squared, I'm just going to use the numbers I have written here, so not rounded. And that is going to give me f net equals 1.5 times 10 to the minus 8 newtons. Okay, so that was very long. Many of these just find the net force type questions are going to be a little bit longer because you have to do this breakdown of the vectors that you have going off at angles into components, and then adding the components and then recombining to get a magnitude, and those steps just are tedious and they tend to take a lot of time. So there's not really any getting around that. Something I will say that is a little bit more typical, especially when you get into doing these types of problems in physics 2, is that there will be some sort of symmetry to the geometry that you have in this question, so that you get certain things, you can just cancel them out visually. I'll show you a little bit of what I'm talking about. So if I had set up this question instead of, let's say, one was at the peak of an equilateral triangle, and then I hope that those are the same distances away. I think they are. And I had put 2 and 3 here. I think those are equidistant. Yeah. Then I would have had f12 going this way and f13 going this way. But if they're all equal masses, and that's kind of the other key thing, is they have to be equal masses, equal distances in order for you to get this kind of nicer quote unquote symmetry. Let's make this cleaner so you can see what the heck I'm talking about. So I'll draw these to be a little bit bigger. So F12, F13, and then if I were to draw the X components of these, F12X, F13X, and then for completeness I'll do the Y components. I'm just not going to include labels because that'll be too messy. So from the symmetry of the question and knowing that M1 equals M2 equals M3, and you can also say the distance between 1 and 2 is going to be equal to the distance between 1 and 3, which would make the magnitude of the forces between these two equal. Well, that also means that also means that these X component magnitudes would have to be equal, but they're pointed in opposite directions, which means that eliminates some of the steps that you would have to do. So if you get a problem like this where from the geometry you can find a symmetry where certain aspects of the forces will cancel each other out, that does save you a few steps, because now you'll only have to find F12Y, F13Y, and then you basically just add those two together and you don't even have to worry about adding components, because your net force ultimately, since these guys are going to be canceling out, our net force is just going to be going straight down. So that makes it a little bit easier. I gave a little bit more of a complicated geometry so that we could go through the basic steps and you could see that. But in physics 2 especially, I think I see more of taking advantage of the geometry of the question to make things easier for yourself. So that's just something to keep in mind. Back to outro, Corinne. Thank you so much for checking out my solutions. Hopefully they helped you, and you can always come back and watch them if you need to see them over again or just need to revisit how some of these topics and how some of these concepts are applied. Tune in next week for more problems and more solutions and some more Sleepy Howitzer if he's willing. And until then, happy physicsing. You say bye to the kiddos. Wish them good luck. Happy physicsing from Howitzer.